Try, right now, to picture nothing. Not an empty room, not a dark night sky, but true nothing. No space, no light, not even a place where the light would go. You cannot do it. Every time you try, your mind quietly builds a stage to set the emptiness on, and the stage is already something. We were all handed the same story about where everything came from. First there was nothing, and then, somehow, there was a universe. But here is what that story leaves out. In the emptiest patch of space we can find, millions of light years from the nearest star, there is a faint trembling that cannot be switched off, an energy that refuses to fall to zero. We have felt it push two metal plates together in a laboratory. We have measured its fingerprint on the electron to 12 decimal places. Everywhere we go looking for nothing, we find a something that will not leave, which means the universe may never have come from nothing at all, because nothing was never a state that reality was allowed to be in. Get comfortable. Hit subscribe if you're new here, because by the end of this, the word nothing will never sound empty to you again, and the beginning of everything will start to feel less like a moment behind you and more like a floor beneath you. Now, let's slowly ease into this. Part 1. The void you think you know. Close your eyes for a moment and try to picture nothing. Most of us reach for the same image without even trying. We picture a black emptiness, a silent darkness stretching in every direction, a space with nothing in it. We imagine the universe before the universe as an empty stage waiting for the first actor to walk on, a blank page waiting for the first word. It feels like the most natural picture in the world. Before there was something, there was nothing, and then somehow the nothing became a something, and here we all are. You have carried that picture your entire life, and almost no one has ever asked you to question it. It sits underneath everything else you believe about where you came from. It is the quiet assumption behind the phrase, the beginning of time, behind the words, the birth of the universe, behind every documentary that opens with a hush and a single point of light appearing in the dark. The nothing comes first. The something arrives later. That is the story we were handed, and we accepted it because it matched an instinct we already had. But here is what that instinct leaves out. That black emptiness you just pictured is not nothing. It is a room. It is space. And space is already a something. The darkness you imagined has dimensions. It has a left and a right, an up and a down, a here and a there. You cannot picture true nothing, because the moment you try, your mind quietly builds a stage to put the nothing on, and the stage is already more than nothing will allow. The emptiness in your head has a shape, and true nothing is not allowed to have a shape. This is where the whole story starts to come apart, gently, the way a knot loosens when you stop pulling on it. We think we understand the word nothing. We use it every day. There is nothing in the fridge. There is nothing on television. There is nothing wrong. But every one of those nothings is a something with the interesting parts removed. An empty fridge is still a fridge full of air. An empty room is still a room full of space, full of light, full of the faint hum of the world outside. When a scientist or a philosopher talks about the nothing that might have come before the universe, they mean something far more severe than an empty room. They mean no space, no time, no fields, no laws, no stage at all, and no darkness to hang on the walls of the stage, because there are no walls. There is not even a place where the universe is not. Try to hold that in your mind, and you will feel it slip away, because your mind is not built to hold it. And that failure, that slipperiness, is not a weakness in you. It may be a clue about the universe. Tonight we are going to follow that clue as far as it goes. We are going to take the most familiar story you know, the story of everything coming from nothing, and we are going to ask a simple, stubborn question. Could it actually have happened that way? Could there really have been nothing, in the severe and total sense, and then a universe? Or is it possible that nothing, real nothing, is not a thing that reality is ever allowed to be? Not a place it can visit, not a state it can occupy, not even for an instant. Because if that is true, then the question you have asked since childhood quietly turns inside out. The question was always, how did something come from nothing? But if there was never any nothing to come from, then something was always here. Something had to exist before the universe, not as a guess, not as a mystery for priests, but as a requirement written into the way reality works. And the moment you accept that, a new and stranger question opens up in its place. If something was already here, what was it? And did it leave anything behind that we could still find? We will get to the fingerprint. There is one, or there might be one, sitting in the oldest light in the sky, and there are people alive right now building the instruments to read it. But we are not there yet. First, we have to take apart the void you think you know, because everything else depends on seeing why that comfortable black emptiness was never really empty at all. So settle in and let the familiar picture start to dissolve, because the first thing we are going to lose tonight is the one idea you were most sure of. Not that the universe had a beginning, something far more unsettling than that. Part 2. The beginning that isn't one. Let us start with what we actually know, because we know a great deal, and it is genuinely one of the most impressive achievements in the history of our species. Roughly 13.8 billion years ago, the universe was hotter and denser than anything you can imagine, and since then, it has been expanding and cooling. We can say that number with real confidence. The best measurement we have puts the age of the universe at 13.787 billion years, give or take about 20 million years, which sounds like a lot until you realize it is a precision of better than 1 part in 600. We did not guess this. We measured it by reading the faint heat left over from the early universe, a subject we will come back to again and again tonight, because that faint heat turns out to be the most important surface in this entire story. It is worth pausing on how we know the universe is expanding at all, because the whole account rests on it, and it is not something anyone simply decided to believe. Almost 100 years ago, astronomers began to notice that the light from distant galaxies was shifted toward the red end of the spectrum, stretched to longer wavelengths, and the farther away a galaxy was, the more its light was stretched. A Belgian priest and physicist named Georges Lemaitre, working in the late 1920s, realized what that pattern meant. The galaxies were not simply moving away through space like debris. Space itself was expanding, carrying the galaxies apart, stretching the light in transit as it traveled. If that is true today, then in the past everything was closer, and the universe had a hot, dense history. Lemaitre followed the logic to its end, and proposed that the whole cosmos had expanded from what he called a primeval atom, a single dense beginning. He was, in a sense, the first person to take the idea of a cosmic origin seriously as physics rather than as story, and every measurement since, of galaxy after galaxy, of the ancient heat itself, has confirmed the expansion he inferred. So when we run the film backward toward the beginning, we are not indulging a fantasy. We are following the most carefully measured trend in all of cosmology to the place where it points. And the place it points is a moment of extraordinary heat and density that our equations cannot quite reach. The picture is often called the Big Bang, and the name does us a disservice because it makes you imagine an explosion. An explosion happens at a place, in the middle of space, throwing debris outward into the room around it. That is not what this was. The expansion of the universe is not stuff flying apart through space. It is space itself stretching, everywhere at once, carrying everything along with it. There was no center, there was no edge, there was no outside for the bang to bang into. Every point was expanding away from every other point, and it still is, right now, as you listen. Now run that film backward. If everything is getting farther apart as time goes forward, then everything was closer together in the past. Keep rewinding. The universe gets hotter, denser, more compressed. Galaxies dissolve back into gas. Atoms come apart into their pieces. The pieces come apart into a searing plasma. And if you keep going, if you trust the equations and rewind all the way, they tell you that a finite time ago, everything in the observable universe was compressed into a single point of infinite density and infinite temperature, a point where the mathematics screams. That point has a name. We call it the singularity, and for a long time people spoke about it as if it were the beginning. Time zero, the first moment, the instant of creation. You have heard it described that way, and it sounds authoritative, and it is almost completely wrong. Here is the thing that took me a long time to properly understand, and that changes everything once it lands. A singularity is not a place, and it is not a moment. It is a message. When the equations of general relativity, the equations Einstein gave us to describe gravity and space and time, spit out the word infinity, they are not telling you what happened at the beginning. They are telling you that they have stopped working. Infinite density is not a physical answer. It is the sound a theory makes when you push it past the edge of what it can describe. It is the equivalent of your calculator showing an error message. The error message is not a fact about the universe. It is a fact about the calculator. Think about what it means when a scientist says the equations break down. It does not mean reality breaks down. Reality was under no obligation to be described by our equations in the first place. It means we have driven our best current theory to the exact point where it fails, and beyond that point we are, for now, without a map. The singularity is not the beginning of the universe. It is the beginning of our ignorance. Those are very different things, and the difference is the whole reason this video exists. So when someone tells you that before the Big Bang there was nothing, ask them how they know. Because the honest answer is that our theory of the very early universe hands us a broken equation right at the moment we most want an answer. And a broken equation is not an answer. It is a signpost. And the signpost does not say, the road ends here. It says, our map ends here. There may be a great deal of road left. This is the first crack in the comfortable story, and I want you to feel how quiet it is. Nobody had to prove that something came before. All we had to notice was that the thing everyone called the beginning was never really a beginning at all. It was the place our understanding gave out. The word before might still be waiting on the other side of that signpost, and the rest of the night is about walking up to it. But to walk past the signpost, we need a better tool than the one that broke. And it turns out we already have one, and it has been sitting in plain sight this whole time, describing the emptiest space you can find. Because the next crack in the story is not about the beginning of the universe at all. It is about whether empty space was ever actually empty. Part 3. You cannot turn space off. Let us leave the beginning of the universe alone for a moment, and go somewhere much easier to reach. Let us go to an empty patch of space, not empty like a room, with air and dust and light passing through it. I mean the emptiest place you can point to in the real universe. Go out past the edge of our galaxy, out past the neighboring galaxies, into one of the immense underdense regions between the great filaments of the cosmos, where the nearest star is millions of light years away in every direction. Draw an imaginary box out there, 1 centimeter on each side, and remove everything from it. Take out every atom, every particle of dust, every stray photon of light. You now have a cubic centimeter of true vacuum, as close to nothing as the universe actually contains. Here is the question that quietly rewrote physics. Is that box empty? Every instinct says yes. You took everything out. What could possibly be left? But the answer, worked out over the last century, and confirmed to a precision that borders on the absurd, is no. That box is not empty. It cannot be empty. And the reason why is one of the most important ideas humans have ever had, so let us take it slowly. In modern physics, the fundamental things are not particles. This is the first shift you have to make, and it is worth pausing on, because most of us were taught the opposite. We were taught that everything is made of tiny particles, little balls of matter, and that is close enough for everyday life, but it is not what the deepest theory says. The deepest theory says the fundamental things are fields. A field is something that has a value at every point in space. You already know one field intimately, even if you have never called it that. A magnet fills the space around it with a magnetic field, an invisible influence that has a strength and a direction at every point, and you can feel it grab another magnet across an empty gap. That influence is not the magnet. It is a field, and it is really there, in the space, doing something. Now, the discovery of the last century is that everything is like this. There is an electron field that fills all of space, and a particle we call an electron is just a little ripple, a concentrated excitation in that field. There is a field for light, and a photon is a ripple in it. There is a field for every kind of particle we know. Reality, at bottom, is a set of these fields, laid over one another, filling every point of space, and the particles you are made of are the ripples running across them. I want you to feel how completely this rearranges the picture you grew up with, because it is easy to nod along and miss the strangeness. You were taught that matter is the solid thing and empty space is the backdrop, the nothing in between the somethings. Quantum field theory turns that inside out. The field is the solid thing, the permanent thing, present everywhere without exception, and matter is the temporary thing, the passing disturbance. Think of the ocean. The water is always there, filling the whole basin, whether or not any wave is crossing it. A wave is not a separate object that arrives from elsewhere. It is a shape the water briefly takes, a pattern of the medium, and when it passes, the water remains, still full, still there. Particles are like that. An electron is a wave the electron field is briefly making. When the electron is absorbed or annihilated, the field does not empty out. It settles back to its quiet, lowest state, still filling all of space, waiting. So the question of what happens when you remove all the particles from a region answers itself once you see it this way. You can remove every wave from the ocean, and you have not removed the ocean. You have only made it calm. And a calm ocean is still, unmistakably, full of water. So when you emptied your box, you removed the ripples. You took out the excitations. But you did not and could not remove the fields themselves. The fields are the space. They are still there in your box, lying quiet, at their lowest possible energy. And here is where it gets genuinely strange, because you might think a field, at its lowest energy, would simply sit at zero, flat, still, doing nothing. That is exactly what you cannot have. The reason is a principle you may have heard of, the uncertainty principle, discovered by Werner Heisenberg in 1927. And it is not a statement about our clumsy instruments. It is a statement about what is allowed to exist. The uncertainty principle says that certain pairs of properties cannot both have perfectly definite values at the same time. For a quantum field, the two properties are its value and its rate of change, and the principle forbids them from both being exactly zero at once. A field that sat perfectly still at perfectly zero, everywhere, with no fluctuation, would have both its value and its motion pinned down exactly, and the universe does not permit that. It is against the rules. So the field cannot hold still. Forbidden from being perfectly zero and perfectly calm, it does the only thing left to it. It trembles. It carries a residual, permanent energy that can never be removed, called the zero-point energy, and it fluctuates, endlessly, at the smallest scales. Empty space is not a flat, calm nothing. It is a restless, shimmering medium, humming with an activity that cannot be switched off, because switching it off would break the most well-tested principle in all of physics. This is the sentence I want you to carry with you through the rest of the night, because we are going to return to it when the stakes are much higher. You cannot turn space off. There is no dial that takes the fields down to nothing. The vacuum is not the absence of everything. It is the quietest possible presence of everything, which is a completely different thing. And I want to head off the natural objection, because it is a good one. You might reasonably wonder whether this is just a limit on what we can know, rather than a fact about what is real. The uncertainty principle is sometimes taught badly, as if it were only about the clumsiness of our instruments. The idea that to measure something you have to poke it, and the poking disturbs it. That version is wrong, and the difference matters enormously here. The uncertainty principle is not a statement about the limits of our measuring devices. It is a statement about what states the universe is allowed to be in at all, whether or not anyone is looking. A field pinned to exactly zero, with exactly zero motion, is not merely a state we cannot verify. It is a state that does not exist, forbidden by the same mathematics that correctly predicts the behavior of every atom and every laser and every transistor in the device you are listening on. So the restlessness of empty space is not our ignorance about the vacuum. It is a real, physical, permanent feature of the vacuum, as real as the charge on an electron, and it would be there in a universe with no observers in it at all. The nothing is a something, whether or not anyone is watching, which is exactly what you would want a real thing to be. Now let me show you what that quiet presence looks like, because I do not want you to take this on my word, and honestly I do not want you to take it on the theory's word either. I want you to see it. Imagine you could be given new eyes, eyes that see quantum fields the way ordinary eyes see light. You are floating in that cubic centimeter of the emptiest space in the universe. To your old eyes it was perfect blackness, perfect silence, the very picture of nothing you started the night with. But with these new eyes, the blackness is gone. Everywhere you look, the fields are shivering. The whole medium is alive with a fine, ceaseless motion, like the surface of water in a glass that will not stop trembling no matter how still you hold it. And through that trembling, pairs of faint ripples are flickering into being and vanishing again, appearing and annihilating before they have fully finished existing. A constant soft sparkle of particles that borrow a moment of existence from the fluctuations and pay it back before the universe can notice. It never stops. It never rests. There is no corner of the box where the trembling ceases and true stillness begins. You are looking at the emptiest place in reality, and it is the busiest thing you have ever seen. This is the floor of the world. This is what is underneath everything, and it is anything but nothing. Open your old eyes again, and the box looks black and silent once more. But you know now what it was hiding. The stillness was a story your senses told you. The truth was underneath the whole time. And if empty space can never truly be empty, if the fields are always there and can never be brought to nothing, then a question begins to form at the edge of all this, quiet and enormous. What happens to our tidy little picture of nothing coming first? Because we just went looking for nothing in the emptiest place the universe has to offer, and we could not find it. We found a something that refuses to leave. The next step is to prove that this restless something is not a theorist's fantasy, and for that, we need to weigh the emptiness and watch it push back. Part 4. The weight of empty space. I know how this sounds. A shimmering medium, filling all of empty space, particles flickering in and out of existence, a trembling that can never be stilled. It sounds like something a physicist made up to sell a story. If empty space were really seething with all this hidden activity, you would expect it to do something. You would expect to be able to catch it in the act. You can. And the fact that you can is the reason we take any of this seriously. Because in physics, an idea is only worth as much as the measurements that back it. And the activity of the vacuum has been measured over and over, in ways that agree with the theory to a precision almost nothing else in science can match. Let me give you 3 of them, and let them accumulate, because the weight of the case is in the stacking. The first was predicted in 1948 by a Dutch physicist named Hendrik Casimir, and it is beautifully simple. Take 2 flat metal plates, ordinary uncharged plates, and bring them very close together in a vacuum, closer than the width of a hair. Now, remember that the vacuum between and around them is full of those fluctuating fields, trembling at every possible scale. But between the plates, in that narrow gap, only some of those fluctuations fit. The gap acts like the body of a flute. Only certain notes are allowed to sound inside it, while outside the plates, in the open, every note is allowed. That means there is slightly more of this vacuum activity pressing on the plates from the outside than from the inside. The result is a real, measurable force pushing the 2 plates together, not because anything charged them, not because of any known attraction between the metals, because the emptiness around them pushes harder than the emptiness between them. For decades this was a prediction on paper, elegant but hard to test, because the effect is tiny and the plates have to be almost impossibly clean and flat and close. Then in 1997, a physicist named Steve Lamoureux measured it directly and found the force right where Casimir said it would be, agreeing with the prediction to within about 5%. The following year, Umar Mohideen and Anushri Roy tightened it further. The vacuum was pushing 2 solid objects together in the laboratory, and the push matched the theory of a space that is anything but empty. You can build a machine whose behavior only makes sense if nothing is a something. The second piece of evidence is older, and in a way, it is even more intimate, because it is about the atoms you are made of. In 1947, 2 physicists, Willis Lamb and Robert Rutherford, measured the energy levels of hydrogen, the simplest atom there is, 1 proton and 1 electron. The theory of the time made a clean prediction about where those energy levels should sit. The measurement came back slightly, stubbornly off, not by much, but by enough that it could not be ignored, and the discrepancy became one of the great puzzles of the moment. The answer, when it came, was the vacuum. The electron in a hydrogen atom is not sitting alone in empty space. It is constantly being jostled by the fluctuations of the fields around it, nudged and shaken by the restless vacuum, and that ceaseless jostling shifts its energy by exactly the tiny amount that was measured. We now call it the Lamb shift, and it was one of the discoveries that launched the entire modern theory of how light and matter interact. The trembling of empty space leaves its mark on the structure of every atom in your body. The third piece is the one that, to me, closes the case, because it is the most precisely tested prediction in the history of science, and the vacuum is baked right into it. Every electron behaves a little like a tiny magnet, and you can ask exactly how strong that magnet is. The simplest theory gives one answer, but the electron, like the one in the hydrogen atom, is never truly alone. It is perpetually interacting with the fluctuating vacuum around it, surrounded by a haze of those flickering virtual ripples, and all of that activity changes the strength of its magnetism by a small, calculable amount. When you include the vacuum, theory and experiment agree to better than 1 part in a trillion. 12 digits of agreement. That is like measuring the distance from New York to Los Angeles and being right to within the width of a human hair. And every one of those digits is only correct because the calculation accounts for the activity of empty space. If the vacuum were truly nothing, the number would be wrong, and it would be wrong immediately, in the 4th or 5th digit. Instead, it is right, 12 digits down, because the nothing is a something, and we have measured the something with a precision that should make you a little dizzy. There is a 4th piece of evidence, quieter than the others, and it is happening inside you right now. Every atom in your body that glows, every light that has ever been emitted by anything, depends on the vacuum. When an atom drops from a higher energy state to a lower one and releases a photon of light, we call it spontaneous emission, and for a long time the word spontaneous hid a puzzle. Why should the atom drop when it does? What tips it over? Left perfectly alone in a truly empty space, an excited atom would have no reason to release its light at any particular moment. The answer, once again, is that the atom is never perfectly alone. The fluctuations of the vacuum are always there, jostling it, and it is those fluctuations that coax the photon loose. Every candle flame, every glowing filament, every star in the sky, shines partly because empty space will not hold still. The light you are seeing by, if you are seeing by any, was in some measure triggered by the restlessness of the nothing. It is not an exotic laboratory curiosity. It is the reason the visible world is visible at all. So let this settle, because it is the emotional turn of the whole night, and it is worth slowing down for. We did not stumble onto a clever theory that suggests empty space might have some energy. We built machines that feel the push of the vacuum. We found its fingerprints in the atoms of our own bodies. We measured its effect on the electron to 12 decimal places. Everything we can touch and test agrees. There is no such thing, anywhere, ever, as genuine nothing, not in the emptiest reach of intergalactic space, not in the cleanest vacuum a laboratory can build, not, as we will see, in the moment before the universe began. And I want you to notice what that does to the picture you started with. You have spent your whole life assuming that nothing is the natural state of things, the default, the blank canvas, and that something is the surprise that has to be explained. Where did all this come from, we ask, as if emptiness were the obvious baseline and existence were the anomaly that needs a reason. But the physics quietly turns that upside down. Nothing is the state that cannot exist. Nothing is the thing that is forbidden. Existence is not the exception that needs explaining. Existence, it turns out, may be the only option the universe was ever allowed. Sit with that inversion for a moment, because it changes what question we should even be asking. We were asking how you get something from nothing, but if nothing was never on the table, then the something was never in doubt. The only real question left is what the something was, and how it became the particular universe we live in. And that question has an answer that is stranger and more satisfying than the empty stage we started with. Because it turns out, the Big Bang was never the moment the fields switched on. It was the moment they changed their mind. That is where we are going next, and it is the idea that turns before the universe from a mystery into a fire with a very specific spark. Part 5. The fire, not the building. If the fields were always there, and the fields are the true substance of reality, then something about the Big Bang has to change in your mind, and it is worth being careful about exactly what. We usually imagine the Big Bang as the moment everything came into existence. The fields, the space, the laws, the whole apparatus of reality, all of it flashing into being at once from a single point. But we have just spent 2 chapters showing that the fields cannot be switched off, that empty space is never truly empty, that nothing is a state reality is not allowed to occupy. If all of that is true, then the fields did not come into existence at the Big Bang. They could not have arrived at the Big Bang, because there is no version of reality in which they were absent and then present. So what, exactly, happened at the beginning that everyone calls the beginning? The answer that modern cosmology gives is subtle and, once you see it, hard to unsee. The Big Bang was not the creation of the fields, it was a change in their state. The fields were already there. What happened is that they went from one configuration to another, and the transition released an enormous amount of energy, and that release is what we see, looking back, as the hot, dense early universe. The stage was not built at the Big Bang. The stage was already standing. What happened at the Big Bang is that the stage caught fire. Let me make this concrete, because it is one thing to say the fields change state, and another to picture it. The leading theory of the very early universe is called inflation, and while the details are still argued over, the core image is clear enough. Imagine one particular field, filling all of space, sitting not at its lowest energy, but perched up on a kind of plateau, holding a great deal of energy in a smooth, calm configuration. A field in that state has a strange property. Its energy does not dilute as space expands the way ordinary matter does. Instead, it drives space to expand, faster and faster, doubling and doubling in size in a fraction of a second. That is the inflationary burst, and it takes a tiny, possibly featureless patch and blows it up into something at least as large as everything we can see. But a field perched on a plateau does not stay there. Eventually it rolls down, off the high smooth ledge and into the valley of its lowest energy, and as it rolls, it sheds the enormous energy it was holding. That energy does not vanish. It pours into the other fields, exciting them violently, filling space with a searing bath of particles, an ocean of light and matter at unthinkable temperature. Physicists call that moment reheating, and it is the closest thing the theory has to what we colloquially mean by the Big Bang. It is the instant the calm, high-energy configuration collapsed into a roaring hot one. It is the moment the fire started. The reason so many physicists take this picture seriously is that it does not just push the beginning back a step for the sake of it. It solves problems the older, simpler story could not. When you look at the ancient light, the universe is astonishingly uniform, the same temperature in every direction, to better than 1 part in 100,000, even in regions so far apart that, in the simple picture, they could never have exchanged heat or light or anything else. How did they come out the same temperature if they were never in contact? Inflation answers this cleanly. Those regions were in contact, close together, sharing conditions, before inflation blew them apart to opposite ends of the sky. The uniformity is a memory of a togetherness that came before the expansion. The same burst also explains why the universe is so precisely flat, why its overall geometry sits on a knife edge that the simple story cannot account for, because inflation stretches any curvature, smooth the way blowing up a balloon flattens the patch of surface under your thumb. So the pre-existing state we are talking about is not an idle add-on. It is doing real explanatory work, tidying up features of our universe that would otherwise be baffling coincidences. The something that came before is not just permitted by the physics. In this picture, it is required to make our own universe make sense. Notice what this does to the whole story. The heat, the density, the expansion, the entire hot early universe that we can measure the leftover glow of, all of it is the fire. And a fire is not the beginning of the building. A fire is something that happens to a building that already exists. The wood was already there. The room was already there. The Big Bang, in this reading, is not the moment reality was created. It is the moment a pre-existing reality changed its state and released its energy, and everything we call the universe is the light of that transition, still traveling outward, still cooling, still expanding, 13.8 billion years later. I want to take you to that moment because it is one of the strangest scenes in all of physics, and I think you should get to stand inside it. Imagine you are there, an instant before the Big Bang, not in a black void, not in nothing, because we have already agreed there is no such place. You are standing inside a field. All around you, in every direction, the field holds still and taut, loaded with energy, smooth as a held breath. There is no explosion yet. There is no heat yet. There is only this immense, patient, poised stillness, a whole reality wound tight and waiting. And the strangest part is how quiet it is, how calm, right at the edge of everything that is about to happen. And then the field begins to move. It rolls, and where it rolls, the stillness breaks open into light. The energy it was holding floods out all at once, and space fills with fire, a heat beyond any furnace, particles boiling into existence by the uncountable trillion, the whole configuration you were standing in erupting into the hot, dense brilliance we have spent a century trying to look back at. You are not watching a universe being born from nothing. You are watching a universe that already existed change its mind, all at once, into the one you live in now. The calm was always there before the fire. The fire is only what the calm became. And this is the phrase I want you to keep, because we are going to need it at the very end of the night, when the stakes are as high as they get. The Big Bang was the fire, not the building. The building was already standing. All the fire did was light it. Which leaves us facing the real question, the one this whole night has been quietly walking toward. If the building was already standing, if something was already here before the fire, then what was it? What is the something that had to exist before the universe? And it turns out that when you ask the serious people, the ones who have spent their lives on this, you get several different answers. But underneath the disagreement, they are all saying the same astonishing thing. Part 6. Then something was already here. Let me say the claim out loud now, plainly, because we have earned it. Something had to exist before the universe. Not as a mystical statement, not as a matter of faith, as a consequence of the physics we have been building, brick by brick, all night. Nothing is a state reality cannot occupy. The fields cannot be switched off. The Big Bang was a change of state, not a creation. Put those together, and you are forced to a single conclusion. There was a something, and the universe as we know it came out of it. Now, the honest situation is that we do not yet know for certain what that something was. This is a live scientific frontier, not a settled textbook chapter, and I am not going to pretend otherwise, because pretending would be a betrayal of the whole spirit of this. But here is what I find genuinely beautiful, and it is the point of this chapter. When you gather up the serious candidates, the real models that real physicists work on, they disagree about almost everything, except the one thing that matters most to us tonight. Every single one of them replaces the nothing with a something. Not one of them starts from true emptiness. They cannot, because true emptiness is not allowed. So let me walk you through the gallery, quickly, not to crown a winner, but so you can feel the agreement underneath the disagreement. The first candidate is the one we have been leaning on, and it is the simplest. The something is just the fields themselves. The quantum fields fill all of space, and always have, at their restless lowest energy, and our Big Bang was a local change in their state, a patch of the eternal field configuration rolling and reheating. In this picture, you do not need a prior universe or an exotic story. You need only the fields, which cannot be zero, doing what fields do. The substrate is the vacuum itself, and the vacuum was never nothing. The second candidate takes that idea and makes it grander. It is called eternal inflation, and it grows out of the work of Alan Guth, who first proposed inflation in 1981, and Andrei Linde and Alexander Vilenkin, who in the early 1980s realized something unsettling about it. Once inflation starts, in most versions it never entirely stops. The inflating state is so good at driving expansion that it keeps going forever across most of space, and every so often, here and there, a patch drops out of it, rolls down, reheats, and becomes a universe like ours. In this picture, our Big Bang is one bubble that stopped inflating inside an endless inflating ocean that is still going right now. Before our Big Bang was the eternal inflation. The something is a background that never began and never ends, budding off universe after universe, ours being merely one. The third candidate is even more direct about the before. It says there was a previous universe. In a family of models called bounce cosmologies, most carefully worked out in an approach called loop quantum cosmology by Martin Boyerwald in 2001 and developed by Abhay Ashtekar and others, gravity itself changes character at extreme density. Instead of collapsing all the way to an infinite singularity, matter reaches a maximum possible density, an almost unimaginable floor of roughly 5 times 10 to the 96th kilograms per cubic meter, and then rebounds. In this picture, run our expanding universe backward, and it does not hit a singularity at all. It hits a bounce. Before our Big Bang was a previous universe, contracting, squeezing down to that density floor, and then springing back outward into ours. The something is an entire prior cosmos, and the Big Bang was its rebound. The fourth candidate is the most poetic, and it comes from Roger Penrose, who won a share of the Nobel Prize in 2020 for unrelated work on black holes, and who has spent years on an idea he calls conformal cyclic cosmology. In this picture, the universe goes through endless cycles, which he calls aeons. Each aeon expands forever, until all its matter has decayed, and all that is left is a cold, empty, formless sea of radiation. And here, Penrose makes a strange mathematical move. He argues that a universe with no matter in it, only radiation, has no way to measure size or time, and so its infinitely large, infinitely old far future becomes mathematically identical to the infinitely small, infinitely hot beginning of a new universe. The end of one aeon is the Big Bang of the next. Before our Big Bang was the exhausted far future of a previous cosmos. And this one, hold on to, because it makes a very specific prediction about the fingerprint we are hunting, and we will come back to it. The fifth candidate imagines that our universe lives on a membrane, a sheet floating in a higher dimensional space, and that our Big Bang was the collision of our sheet with a neighboring one. This is the ekpyrotic idea, proposed by Paul Steinhardt, Neil Turok, and their collaborators around 2001, and in its cyclic versions the sheets collide, bounce apart, drift back, and collide again, over and over. Before our Big Bang was the approach of another world through a dimension we cannot see. The something is a second membrane, and the Big Bang was the moment it touched ours. I owe you one honest complication before we go on, because it is important, and because leaving it out would make the case sound tidier than it is. Some of these models, especially the ones where inflation goes on forever, run into a subtle mathematical wall. In 2003, 3 physicists, Arvind Borde, Alan Guth, and Alexander Vilenkin, proved a theorem about any universe that has been expanding on average throughout its history. They showed that such a universe cannot be extended infinitely far into the past. Trace it back, and the histories come to an edge, an incompleteness, a place where the classical description simply stops. This is sometimes reported in headlines as proof that even inflation needs a beginning, and that the universe must have started from nothing after all. But that is a misreading, and Vilenkin himself has been careful about it. The theorem does not say the universe began from nothing. It says the classical, smooth description of space-time runs out, exactly the way general relativity runs out at the singularity. It is another signpost, not another wall. What lies past it is not nothing. It is the regime where quantum gravity takes over, the regime we do not yet have the equations for. So even the theorem that sounds like it demands a beginning is really pointing at the same place everything else tonight has pointed, at a deeper layer of physics beneath the one we can currently describe, a something we have not yet learned to read. Now step back and look at the whole gallery at once, because this is the thing I most wanted you to see: the fields, the eternal inflation, the prior contracting universe, the exhausted previous aeon, the colliding membrane. These models could hardly be more different from one another. Their advocates argue fiercely. Some may be completely wrong, but every one of them, without exception, hands the Big Bang a something to begin with. Not one serious model starts from true nothing, because not one of them is allowed to. The disagreement is only about what the something was. The agreement, underneath, is total. Something was already here. And that agreement, quiet as it is the backbone of the whole night. Physicists who cannot stand each other's theories, who dispute nearly every detail, converge, without meaning to, on the single claim we started from. Existence, not emptiness, is the thing that never needed a cause. The universe was handed something to begin with. And if it was handed something, if a real physical state came before the fire, then a thrilling possibility opens up, the one we have been circling since the first minute. A physical something that existed before our universe is a physical something that could, in principle, have left a physical trace. Not a philosophical argument, a mark, an actual mark, somewhere we could actually look. So where would we look? And has anyone actually found anything? Part 7. If it was real, it left a mark. Here is where the story turns from an argument into a hunt, and I love this turn, because up to now, everything we have said, however carefully, has been reasoning, beautiful reasoning, backed by laboratory measurements of the vacuum, but reasoning all the same. Now we get to ask the question that separates science from philosophy. If something really came before, or underneath, our universe, is there any physical evidence of it? Did it leave a mark we can actually find? And to answer that, we need to know where in the universe such a mark could possibly survive. Think about what we are asking for. We want a trace of the earliest possible state of reality, something from before or during the transition that made our universe. But the early universe was a furnace. For a long time after the Big Bang, everything was so hot and dense that the whole cosmos was an opaque, glowing plasma, a fog of charged particles and light so thoroughly mixed that no signal could travel cleanly through it. Any delicate pattern, any fingerprint from before, would seem to be hopelessly scrambled by that fire. So where could a mark endure? The answer is one of the most important surfaces in all of science, and we have mentioned it several times tonight, without fully meeting it. It is time to meet it properly. For roughly the first 380,000 years, the universe was that opaque glowing fog. Then it cooled to a critical point, around 3,000 degrees, cool enough that the loose electrons and protons could finally join into neutral atoms. And the moment that happened, the fog cleared. Suddenly light could travel freely, and it has been traveling ever since, for 13.8 billion years, stretching and cooling as space expanded, until today it fills the entire sky as a faint hum of microwaves at a temperature of just 2.7 Kelvin, less than 3 degrees above absolute zero. We call it the cosmic microwave background, and it is the oldest light there is. It is a photograph of the universe at 380,000 years old, taken from the inside, wrapped around us in every direction. Every patch of sky, if you had the right eyes, is glowing with it right now. We found this ancient light almost by accident, and the story is worth a moment because it tells you how real it is. In 1965, two engineers at Bell Laboratories in New Jersey, Arno Penzias and Robert Wilson, were working with a large horn-shaped antenna and kept picking up a faint hiss they could not get rid of. It came from every direction in the sky, day and night, in every season. They checked their equipment, they cooled their instruments. They famously cleaned out the droppings of pigeons that had nested in the horn, suspecting the birds were the problem. The hiss remained. What they had stumbled onto, without knowing it, was the leftover heat of the early universe, the cosmic microwave background itself, the very glow that theory had predicted should be there. They won the Nobel Prize for a signal they had spent months trying to eliminate. That is how solid this surface is. It is not a delicate inference at the edge of detection. It is a hum so loud and so everywhere that you cannot build a sensitive radio antenna without hearing it. And every improvement since, from satellites to balloons to the telescopes we will visit at the end of tonight, has only sharpened the picture, turning that hiss into a map of the infant universe, detailed enough to search for the faintest marks of what came before. That ancient light is the closest thing we will ever have to a fossil of the early universe, and it is where any fingerprint of the before would have to show up, because the pattern of that light, the tiny variations in its temperature from place to place across the sky, was set by the conditions in the universe at the very earliest times. Those little hot and cold spots are the seeds from which every galaxy later grew, and they were laid down by processes reaching all the way back toward the transition that made our cosmos. If the something that came before left any imprint, any subtle irregularity, any mark that the fire could not erase, this is the surface it would be written on. Read the oldest light carefully enough, and you might be reading a message from before the beginning. And here is the astonishing thing. The cosmic microwave background is almost perfectly smooth. Almost. Everywhere you look, it is the same faint temperature, to better than 1 part in 100,000, which is itself a profound clue, because a universe that came out of a wild explosion should not be so uniform. But it is not perfectly smooth. There are tiny variations, the hot and cold spots, and overwhelmingly they look exactly the way the standard theory predicts, random and evenly distributed, the frozen ripples of quantum fluctuations from the inflationary era. This is one of the great triumphs of modern cosmology, and I do not want to undersell it. Most of the map looks precisely as it should, but not all of it. And this is where it gets interesting, because scattered across that ancient light are a handful of features that do not quite fit. A cold region, larger than it has any right to be. A strange alignment of the biggest patterns, pointing in a direction they should not care about. A faint lopsidedness between one half of the sky and the other. And, most dramatically of all, a set of curious rings that one Nobel laureate insists are the literal scars of a universe that died before ours was born. Each of these might be nothing. Each might be a statistical fluke, or a smudge of foreground contamination, or an artifact of how we process the data. Scientists argue about every one of them, and they are right to. But each one is also, just possibly, a place where the fire did not quite erase what came before. Each one is a candidate fingerprint. So for the rest of the night, we are going to walk through these anomalies, one at a time, carefully, honestly, separating what is measured from what is claimed. We are going to look at the cold spot that is too cold. We are going to look at the alignment that shouldn't exist. And we are going to look at those rings, the boldest claim of all, the one that says a previous cosmos left its heat printed on our sky. I cannot promise you that any of them is real. The honest state of the science is that none is confirmed. But I can promise you this. For the first time in the history of our species, the question of what came before the universe is not a question for philosophers or priests. It is a question for telescopes. And the first mark we are going to examine is a cold, quiet, enormous patch of sky that has unsettled cosmologists for 20 years. Part 8. The cold spot. In the southern sky, in the direction of the constellation Eridanus, there is a place in the oldest light that is colder than it should be. To find it, you would need instruments no eye can match, because we are talking about temperature differences of millionths of a degree across a background that is already only a few degrees above absolute zero. But the satellites that map the cosmic microwave background, first an American mission called the Wilkinson Microwave Anisotropy Probe, and later the European Planck satellite, have measured that ancient light across the entire sky with extraordinary care. And when they did, they found, sitting in the southern sky, an unusually large and unusually cold region, about 70 millionths of a degree colder than its surroundings, spanning several degrees across, wide enough that you could cover it with a few full moons laid side by side. Cosmologists gave it a plain name that has stuck. They call it the cold spot. Now, you have to understand why this is strange, because on its own, a cold patch in the sky does not sound like much. The whole background is speckled with hot spots and cold spots. That is the expected pattern, the frozen ripples we talked about. The point of the cold spot is not that it is cold. The point is that it is too big and too cold at the same time. In the standard picture, where the spots are random fluctuations, you can calculate how often a cold region, this large and this pronounced, should show up just by chance? And the answer is that it should be rare, not impossible, but uncomfortable. A feature like this sitting in our sky is the kind of thing that makes a cosmologist look twice, and then look a third time, and then start wondering whether something more than chance is going on. I should be fair about how the statistics actually work here, because it is easy to overstate and easy to understate, and the truth sits in an uncomfortable middle. When you first spot an anomaly, you are always at risk of fooling yourself, because the sky is enormous, and you have many places to look. If you scan a whole map for the coldest, largest region you can find, you are almost guaranteed to find something that looks unusual somewhere, in the same way that if you flip enough coins, you will eventually see a long run of heads that means nothing. Statisticians call this the danger of choosing your target after you have seen the data, and the honest cosmologists who study the cold spot know it well. So the real question is not whether the spot looks strange, it is whether it is stranger than the strangest thing you would expect to find by chance in a map that large. And the careful analyses land in a genuinely awkward place. The cold spot is unusual at roughly the 1 in a few hundred to 1 in 1,000 level. Unusual enough to be interesting, not so unusual that it cannot possibly be chance. That is precisely the range where reasonable people disagree, where the same number looks like a tantalizing hint to one researcher and a predictable fluke to another. It is the frustrating middle ground of frontier science, and it is exactly where honesty matters most. So what could make it? The most conservative explanation, the one that requires no new physics at all, is that the cold spot is a shadow. Here is the idea. As the ancient light travels across 13 billion years to reach us, it passes through the large-scale structure of the universe, through regions crowded with galaxies, and regions nearly empty of them. And it turns out that when light passes through an enormous underdense region, a supervoid, a place where there is far less matter than average, it can lose a tiny bit of energy on the way through, because of the way the void's gravity stretches during the crossing. Light that crosses a giant emptiness comes out very slightly cooler. So if there were a supervoid sitting between us and the cold spot, it could chill the light passing through and print a cold patch on our map, with no need for anything exotic in the early universe at all. And there does seem to be a void out there. In 2015, a team led by Istvan Shapudi reported a large underdense region in the direction of the cold spot, sometimes called the Eridanus supervoid, an immense stretch of space with a shortage of galaxies. For a while, this looked like it might be the tidy answer, a giant hole in the cosmos, chilling the ancient light, mystery solved. But it has not turned out to be that simple, and this is where honesty matters. When cosmologists worked through the numbers, many found that the void, real as it is, does not seem to be enough. The chilling effect it would produce falls short of explaining the full depth of the cold spot. The void helps, it may not finish the job, and so the cold spot remains, 20 years after it was first noticed, an open question, a place where the standard story is not quite comfortable. I want to be careful here, because this is exactly the kind of anomaly where it is tempting to leap too far, and part of the discipline of this channel is refusing that leap while still taking the mystery seriously. The cold spot is not proof of anything. The most likely explanation is still some combination of the supervoid and ordinary statistical bad luck, a rare but not impossible fluctuation that happens to sit where we can see it. Most working cosmologists would tell you that, and they would be right to be cautious. A single odd cold patch in a sky full of random spots is not, by itself, a message from before the beginning. But here is the reason we linger on it anyway. There is a bolder idea about the cold spot, one that most cosmologists set aside, but very few can rule out entirely. And it is exactly the kind of thing this whole night has been building toward. What if the cold spot is not a shadow at all, but a bruise? In the picture of eternal inflation we talked about, where our universe is one bubble among endlessly many in an inflating ocean, it is possible for two bubbles to collide. Our universe could, early on, have bumped into a neighboring universe, and such a collision would leave a distinctive mark on the sky, a roughly circular disturbance in the ancient light, a place where another cosmos pressed against ours and left an impression. Some have wondered whether the cold spot could be exactly that, the healed bruise of a collision with another universe. It is a genuinely serious enough idea that people went looking. In 2011, Stephen Feeney and his colleagues searched the cosmic microwave background specifically for the circular signatures that bubble collisions would leave. They combed the ancient light for the telltale rings, and they found nothing that held up. No confirmed collision signature, no verified bruise. The search came back empty, which does not prove that no collision ever happened, only that we have not found the mark of one, and the difference between those two statements is the difference between science and wishful thinking. So where does that leave the cold spot? It leaves it as what it honestly is, an unexplained cold patch that is probably a void and a fluke, but that just might be something stranger, and that nobody has fully closed the book on. It is the gentlest of our candidate fingerprints, the one most likely to dissolve into ordinary physics on closer inspection. I put it first for exactly that reason, because I want you to see how a responsible mystery behaves. It is not a triumphant discovery. It is a loose thread, tugged at for 20 years, still not fully pulled free. And a universe honest enough to leave its loose threads showing is a universe worth trusting when the threads get stranger. The cold spot teaches the posture we need for everything that follows. Hold the mystery seriously enough to keep looking, and hold it loosely enough to let it go if the evidence says so. That balance is the whole discipline, and it is the only thing that separates the search for a real fingerprint from the comfort of seeing what we want to see. Because they are about to get stranger. The cold spot is a single patch, one region that is merely too cold. The next anomaly is not about one patch at all. It is about the largest patterns in the entire sky, lining up in a way that, if it is real, should not be possible, pointing along a direction the universe is not supposed to have. And unlike the cold spot, this one does not go away when you find a nearby void. Part 9. The axis that shouldn't exist. Step back from the individual spots for a moment and look at the whole map of the ancient light at once, at its very largest scales, and something odd begins to emerge, something that has bothered cosmologists more than a single cold patch ever could. To understand why, you have to understand one of the founding assumptions of modern cosmology, an idea so basic that it is easy to forget it is an assumption at all. We assume the universe has no preferred direction. This is sometimes called the cosmological principle, and it says that on the largest scales, the universe looks the same everywhere and in every direction. There is no up for the cosmos as a whole, no special axis, no favored orientation. Every direction is equal. This is not just a philosophical preference. It is built into the equations we use to describe the entire universe, and it has passed test after test. The ancient light, in particular, should be the very picture of this even-handedness. Its largest patterns should be sprinkled across the sky, with no regard for direction, like the pattern of raindrops on pavement, which favors no compass point. But when cosmologists looked carefully at the largest features of the cosmic microwave background, the broadest, most sweeping temperature patterns across the whole sky, they found something they did not expect. Those largest patterns seemed to line up. Instead of being oriented randomly, some of the biggest features appear to share a common direction, arranged along a single axis running across the sky. Two physicists, Kate Land and João Magejo, gave this apparent alignment a memorable name in 2005. They called it the axis of evil, half in jest, because an alignment like this is, from the standpoint of standard cosmology, something close to a sin. The universe is not supposed to have an axis, and yet, in the largest patterns of its oldest light, one seems to appear. It is not the only large-scale oddity, either. When you measure how the temperature of the ancient light at one point on the sky relates to the temperature at points far away, across the widest angles, the standard model predicts a certain amount of correlation. The measurements come back low. There is less large-scale structure in the ancient light than there is supposed to be, as if the biggest ripples were quieter than the theory expects. And on top of that, there is a lopsidedness. One half of the sky appears to have slightly more texture, slightly stronger fluctuations, than the other half. A hemispherical asymmetry that, again, a universe with no preferred direction should not display. Three separate large-scale anomalies, all pointing, in their different ways, at the same uncomfortable possibility. Maybe the largest scales of the universe are not as even-handed as we assumed. Now, I have to give you the deflating explanations, because they are real, and they are probably at least partly right. And leaving them out would be exactly the kind of dishonesty this channel refuses. The first is simple chance. When you are looking at the very largest patterns in the sky, there are only a handful of them to measure. You do not get to average over thousands of independent features the way you do at smaller scales. And when you only have a few things to measure, flukes are easy. An alignment that looks meaningful might just be the kind of coincidence that a small sample throws up now and then, the way a handful of coin flips can come up heads several times in a row without anything being wrong with the coin. Cosmologists call this cosmic variance, and it is the most boring and most likely explanation for at least some of what we see. The second deflating explanation is contamination. We do not observe the ancient light in a clean vacuum. We observe it through our own galaxy, through the dust and gas of the Milky Way, through the motion of our own solar system, through the whole foreground of the local universe. Removing all of that to get at the pristine background is delicate work, and it is possible that some of the large-scale alignments are not in the ancient light at all, but are artifacts left behind by the imperfect subtraction of everything in front of it. An axis that points suspiciously close to features of our own cosmic neighborhood is exactly what you would expect if the alignment were a processing artifact rather than a genuine pattern from the early universe. So the responsible position is that the large-scale anomalies might well be some mixture of chance and contamination, and many careful cosmologists lean that way. But here is why they refuse to fully die, why people keep returning to them year after year. They have persisted. When the American satellite first hinted at these alignments, the natural hope was that the more precise European mission would wash them away, revealing them as noise. It did not. The Planck satellite, with far better instruments, largely confirmed that these large-scale oddities are really there in the data. They are not going away as the measurements improve, which is not what you expect from a simple fluke, and it is not what you expect from contamination that better instruments should remove. The anomalies are stubborn, and stubbornness, in physics, is a reason to keep looking. Because if these alignments are real, if the largest scales of the universe truly do carry a preferred direction, then something set that direction, and it had to be something reaching back to the very earliest moments, before or during the transition that shaped our cosmos. A universe that emerged from a perfectly featureless nothing should be perfectly even-handed on the largest scales. A universe that emerged from a something, a pre-existing state that already had some structure, some orientation, some texture of its own, might carry the faint imprint of that structure written across its largest patterns, a birthmark inherited from before. The axis of evil, if it is real, might be exactly that kind of birthmark, a whisper of the conditions that preceded our beginning, too large to have been created since, pointing back toward whatever came before. There is a reason the largest scales are the right place to look for such a birthmark, and it is worth making explicit, because it is the logic behind the whole fingerprint hunt. The smallest features in the ancient light have been worked and reworked by countless physical processes since the beginning, jostled by the plasma, reshaped by the growth of structure, overwritten again and again. But the very largest patterns, the ones that stretch across most of the visible sky, are too big to have been generated by any process operating since the Big Bang, because no signal could have crossed them in the available time. They are frozen in from the earliest era and essentially untouched since. That makes them a kind of preserved layer, the oldest and least disturbed part of the record, the place where a mark from before the beginning would have the best chance of surviving intact. If you wanted to read the faint handwriting of whatever preceded our universe, you would not look at the fine print, which has been smudged by 13 billion years of history. You would look at the largest letters, which have not been touched since they were written. And it is precisely in those largest letters that the anomalies appear. That may be a coincidence, or it may be the universe showing us its oldest, most protected scar in exactly the place we would expect an old scar to last. I want to be clear one more time, because it matters. Nobody has proven this. The alignments might yet turn out to be chance and dust. But notice how the case is building, not through any single overwhelming discovery, but through accumulation, the way this channel likes to build things. A cold patch too cold to easily explain, a set of large-scale patterns that line up when they shouldn't. Each one alone is dismissible. Together they sketch the outline of a sky that is not quite as random as a universe from nothing should be. And now we come to the boldest claim of all, the one that does not merely hint at a before, but names it, and points to specific rings in the ancient light, and says, without flinching, that they are the heat of a universe that died before ours began. Part 10. The Ghost of a Dead Universe. Everything we have looked at so far has been a hint, a hedge, a maybe. Now I want to tell you about a claim that is not hedged at all, made by one of the most respected physicists alive, who looked at the oldest light and said, in effect, I can see the previous universe from here. His name is Roger Penrose. He is not a fringe figure. He spent decades at the front rank of physics. He proved foundational theorems about black holes and singularities alongside Stephen Hawking, and in 2020, he was awarded a share of the Nobel Prize in Physics. When a mind like that makes an extraordinary claim, you do not dismiss it, even if you end up disagreeing. You listen carefully, and the claim Penrose makes is about as extraordinary as they come. Remember his model, conformal cyclic cosmology, from our gallery of somethings. The universe runs in endless cycles, which he calls eons. Each eon expands forever, until all the stars have burned out, all the matter has decayed, and every black hole has slowly evaporated away into radiation over unthinkable spans of time. What is left at the end of an eon is a cold, thin, formless sea of light, with no matter in it at all. And Penrose argues, through a piece of mathematics we touched on earlier, that such an empty sea, having no way to measure size or duration, becomes indistinguishable from the hot, dense beginning of a brand new universe. The exhausted end of one aeon becomes the Big Bang of the next. And crucially, Penrose says, some information can carry across that boundary. The previous aeon can leave marks on the one that follows, on ours. And then he tells you exactly what marks to look for, which is what makes this real science rather than poetry. Because a claim you can check is a claim with teeth. In the previous aeon, Penrose points out, there would have been enormous black holes, the giants that sit at the centers of galaxies, millions or billions of times the mass of the sun, and over the incomprehensible lifetime of that eon, those black holes would slowly evaporate, releasing their entire mass energy as radiation through the process Hawking first described. When two galaxies merged in that previous universe, their central black holes would have merged too, and the evaporation of such a combined giant would pour out a specific, concentrated amount of energy. Penrose argues that this outpouring, carried across the boundary from the previous eon into ours, would show up in our cosmic microwave background as a particular kind of feature, a roughly circular patch, a point on our sky with a distinctive ring of temperature around it, marking the spot where a black hole from the previous universe finished dying. He calls these features Hawking points. Let me take you to one, because I think you have to feel the strangeness of what is being claimed, not just hear it. Imagine you are looking at a map of the oldest light, the whole ancient sky spread out before you, that familiar speckle of hot and cold, and someone points to one faint, unremarkable spot, a slightly warm point with a soft ring around it, easy to miss among the millions of others. That, they tell you, is not a random ripple. That is the grave of a black hole. Not a black hole in our universe, a black hole in the universe before this one, a giant that anchored some long-vanished galaxy in a cosmos that expanded and cooled and died entirely before our own Big Bang ever happened. Over an eternity you cannot picture, that black hole swallowed the light of a dead cosmos and then, slowly, atom of heat by atom of heat, gave it all back, evaporating into nothing across a span of time, next to which the current age of our universe is less than a blink. And the last of that heat, the final radiation of a monster from the world before, soaked across the boundary between one reality and the next, and printed itself, faintly, on the sky you are looking at now. You are not looking at a smudge in the data. You are looking, if the claim is true, at the ghost of a universe that was already ancient and dead before ours drew its first breath. And it is sitting there, in the light, over your head, on every clear night of your life. Sit with that for a moment, because whether or not it is true, the sheer scale of the claim should stop you. Somewhere in a data file on a scientist's computer, there may be the recorded heat of a universe that lived and died before ours began. Even as a possibility, even as a maybe that might be wrong, the thought that a dead cosmos could leave a scar we can measure, a fingerprint faint but real, is one of the most vertiginous ideas that physics has ever put on the table. This is what we meant, at the very start, when we said something had to exist before the universe. Penrose is not speaking in metaphors. He is pointing at rings in the sky and naming the dead. Now I have to bring you back down, carefully, because this is exactly the kind of claim that demands the most honesty, and Penrose himself would insist on it. The claim is contested, seriously, thoroughly contested. In 2010, Penrose and Vahi Gurzadian reported finding concentric circles of unusually low variation in the ancient light, which they read as early evidence. In 2018, Penrose, together with Daniel Ahn, Krzysztof Meissner, and Pavel Narovsky, published a stronger claim, reporting around 30 candidate Hawking points in the data at a stated statistical significance of roughly 3 standard deviations, which in ordinary terms means a pattern that should occur by pure chance only a few times in 1,000. That sounds impressive, but other teams pushed back hard. They argued that when you generate fake skies using nothing but standard physics, pure random fluctuations with no previous aeon at all, you find features that look just as much like Hawking points as the ones Penrose identified. In other words, the marks might be real patterns in the data that mean nothing. The human tendency to see rings where there are only ripples. And in 2024, a fresh reanalysis found the claimed signal consistent with what a perfectly ordinary universe would produce on its own. No ghost required. It is worth understanding why 3 standard deviations, which sounds so convincing, is not enough to settle a claim like this, because the lesson applies far beyond Penrose. In physics, the bar for announcing a genuine discovery is deliberately set very high, at 5 standard deviations, a level of certainty corresponding to a chance of fooling yourself of less than 1 in a million. 3 standard deviations, the level Penrose reported, corresponds to a chance of a few in 1,000, and the history of physics is littered with 3 sigma results that excited everyone and then evaporated when more data came in. There is a reason for the caution, and it is the same reason we met with the cold spot. When you search a huge sky for a particular kind of pattern, you have so many chances to find something that looks like your target, that patterns meeting a 3 in 1,000 bar will turn up even in a universe where the effect is completely absent. The critics of the Hawking points did not merely wave their hands. They generated artificial skies containing nothing but ordinary random physics, no previous aeon at all, and then ran Penrose's own search on those fake skies and found just as many convincing-looking rings. That is the crucial test, and it is the one the claim has struggled to pass. If your signal shows up just as strongly in a universe you know has no ghosts in it, then your signal is not evidence of a ghost. It is evidence of how good the human eye and the human method are at finding faces in clouds. So where does the honest account land? It lands here. The Hawking points are not confirmed. The majority of cosmologists do not believe our sky carries the heat of a previous eon, and the most recent careful analyses find no signal beyond chance. If I had to bet, I would bet that these particular rings are ripples after all. But, and this is the point of telling you, the claim is real science, made in good faith by a great physicist, and it is exactly the shape of thing we should be looking for. It says, the something that came before was not a vague philosophical necessity, but a physical universe that could leave physical heat on our sky, and it tells us precisely where to look and what to measure. That is not fringe. That is the frontier behaving exactly as a frontier should, with a bold claim, a fierce fight, and a verdict still out. And the fight over these rings forces us, finally, to confront the hardest objection of the entire night, the one that asks whether the word before even means anything at all. Part 11. North of the North Pole. There is an objection to everything we have said tonight, and it is the strongest one, and if I did not raise it, you would be right to feel I had been leading you gently around a hole in the ground. So let me walk you straight to the edge of it. The objection is this. All night we have been asking what came before the universe, and we have been treating before as if it obviously means something, earlier in time, a moment that happened prior to the Big Bang. But what if time itself began with the universe? What if there was no time before the Big Bang? Not because there was nothing, but because before is a word that requires time to be meaningful, and time is precisely the thing that may not have existed yet. If that is so, then asking what came before the universe might be like asking a question that quietly destroys itself, a question that sounds sensible but points nowhere. Stephen Hawking had a favorite way of putting this, and it is worth holding on to because it is genuinely clarifying. He said that asking what came before the Big Bang is like asking what lies north of the North Pole. The North Pole is a perfectly real place. You can stand on it. But the question what is north of here has no answer there, not because the answer is hidden, but because north stops meaning anything once you are at the top of the world. There is no direction more north than the North Pole. Every way you step is south. In the same way, Hawking suggested, if time began at the Big Bang, then before stops meaning anything as you approach it. There is no moment more before than the beginning. Every direction in time is after. And this is not just Hawking being clever. It reaches into the deepest mathematics we have for these questions. When physicists try to combine quantum mechanics with gravity to describe the universe as a whole, they arrive at an equation called the Wheeler-DeWitt equation, and it has a famously disturbing feature. It has no time in it. Time, as a fundamental variable, simply is not there. Many physicists take this to mean that time is not a bedrock feature of reality at all, but something that emerges, the way temperature emerges from the motion of countless molecules, even though no single molecule has a temperature. Down at the very bottom, in the equations that would describe the birth of a universe, there may be no ticking clock, no flow, no before and after, only a timeless structure out of which time itself crystallizes as the universe unfolds. If the idea of time being emergent rather than fundamental sounds impossible, consider how many familiar things work exactly that way. Temperature is not a property any single molecule has. A lone atom does not have a temperature. Temperature only appears when you have a great many molecules together, and it emerges from their collective motion, real and measurable and useful, yet nowhere to be found in the individual pieces. The wetness of water is like this too, and the pressure of a gas, and the flow of traffic on a highway, which is a real pattern with its own behavior, even though no single car is traffic. Physicists increasingly suspect that time is another such emergent property, arising from something deeper, perhaps from the way quantum systems become entangled with one another, real and unmistakable at our level, and simply not present in the foundation. And if that is right, then the human intuition that there must have been an earlier moment, a before, is exposed as exactly that, a habit of minds that live inside time and cannot easily imagine anything else. The philosopher and theologian Augustine, writing more than 1500 years ago, arrived at a version of this by pure thought, arguing that there was no time before the world because time itself came into being with the world, so there was no then when there was no time. He had no equations. He had only the same vertigo you are feeling now, and he followed it honestly to nearly the same place the mathematics points today. Now, you might think this destroys everything we have built. If before means nothing, then how can something have existed before the universe? And here is the turn I most want you to follow, because it does not destroy the claim. It sharpens it, and it makes it stranger and more intimate than it was. When we said something had to exist before the universe, we were using the only word our time-bound minds have for the relationship. But the physics does not actually require that the something sat at an earlier moment. It requires that the something is more fundamental than our universe, that it underlies our universe. The fields we cannot switch off, the timeless quantum structure of the Wheeler-DeWitt equation, whatever the true substrate turns out to be, it does not have to live in the past. It may live beneath, not before in time, but deeper than time. Our whole universe, space and time included, may be something that emerges from that deeper structure, the way a wave emerges from the sea, and the sea is not earlier than the wave. It is under it, around it, holding it up, right now. Do you feel how that changes things? We began the night imagining the origin as a moment, far behind us, at the end of a long rewind, a lost first instant at the far end of the past. And the honest physics suggests something almost tender instead. The something that had to exist before the universe may not be a lost moment behind you at all. It may be a present tense foundation beneath you, holding everything up as you listen, closer than any past could ever be. The beginning did not happen once and vanish. If time emerges from a deeper substrate, then that substrate is still here, still underneath, still doing the thing it does. The origin never left. You are standing on it. You have been standing on it your entire life. Return to the ocean for a moment, because the picture completes itself there. A wave on the sea is not older or younger than the water beneath it. It rises out of the water, is made entirely of the water, and sinks back into the water, and at no point is the sea located in the wave's past. The sea is under the wave, around the wave, holding the wave up for as long as the wave exists. If our universe is a wave, space and time, and everything in them a shape the deeper substrate is briefly making, then the substrate is not our history, it is our flaw, and that changes the emotional weight of the entire question. To ask what came before the universe, imagining a lonely first moment, lost at the far end of an unimaginable past, is to feel small and orphaned, cut off from an origin you can never reach. But to understand that the origin is beneath you, present tense, holding you up right now, as surely as the sea holds the wave, is a different feeling entirely. You are not the distant descendant of a beginning that happened once and vanished. You are a shape the foundation is making, this instant, and the foundation has not gone anywhere. It could never have been nothing, and it never stopped being everything underneath. This is the reframing I promised you at the start, when I said we would keep the phrase, before is not earlier, it is deeper, and let its meaning grow. It started as a small hint, back when we called the singularity a signpost rather than a beginning. Now it can stand up straight. The question what came before the universe was never really about the past, it was about the foundation. And the foundation is not gone. It is the quietest, most permanent presence there is. The floor beneath the floor, the something that cannot be nothing, holding the wave of your universe aloft. And this deeper substrate leaves us with one last, humbling problem, because we can prove it must exist, and we have measured its restlessness in the laboratory to 12 decimal places, and yet when we try to calculate the most basic thing about it, how much it should weigh, we get an answer so catastrophically wrong that it stands as the largest failed prediction in the history of physics. We are certain the something is there. We have almost no idea what it truly is, and the number that proves how little we understand it is waiting in the next part. Part 12. The number that breaks the vacuum. I have spent this whole night telling you how sure we are that empty space is a something. The fields cannot be switched off. The vacuum has energy. We have measured its push, felt it in the atom, confirmed it to 12 digits. You cannot turn space off. I have said that phrase several times, and every time I meant it as a statement of confidence. Now I have to turn it over and show you the other face of it, because the same vacuum we understand so precisely also hides the single most embarrassing number in all of physics. Here is the problem. If empty space has energy, then we ought to be able to calculate how much. We know the fields. We know they fluctuate. We can add up the energy of all those fluctuations, all the trembling of the vacuum at every scale, and arrive at a number for how much energy a chunk of empty space should contain. Physicists have done this calculation, and separately, we can measure how much energy empty space actually contains, because that energy has a gravitational effect. The energy of the vacuum pushes space to expand, and we can observe that push directly. In fact, we discovered, in the late 1990s, that the expansion of the universe is accelerating, driven by exactly this kind of energy woven into empty space, which we now call dark energy. So we have a prediction from theory and a measurement from the sky. We can compare them. They do not agree, and they do not disagree by a little. When you calculate how much energy the vacuum should have, and you compare it to how much it actually has, the theoretical number is larger than the measured one by a factor so enormous that it barely fits in the mind. Depending on how you set up the calculation, the prediction overshoots reality by up to 120 orders of magnitude. That is a 1 followed by 120 zeros. It is not a rounding error. It is not a factor of 2 or 10 or a million. It is the worst prediction in the history of science, the largest gap between theory and observation that physics has ever produced, and it sits right at the center of the thing we have been most confident about all night. We call it the cosmological constant problem, and after decades of the finest minds in physics working on it, it remains unsolved. The discovery that made this problem unavoidable is worth telling, because it turned an abstract worry into a measured fact. In the late 1990s, two competing teams of astronomers set out to measure how fast the expansion of the universe was slowing down. Everyone assumed it must be slowing, because gravity pulls everything together and should be gently applying the brakes. Both teams measured distant exploding stars to track the expansion across billions of years, and both got the same shocking answer. The expansion is not slowing down. It is speeding up. Something is pushing space apart, overpowering gravity on the largest scales, and that something behaves exactly like energy, woven into empty space itself, the very vacuum energy we have been discussing. The result was so unexpected that it earned a Nobel Prize, and it forced the vacuum energy from a theoretical curiosity into a number we have actually observed in the sky. And that is what makes the 120 orders of magnitude so painful. It is not that we cannot find the vacuum's energy. We have found it. We can see it accelerating the universe. It is that the amount we see is fantastically smaller than the amount our theory says it should be. Small, but not zero, tiny, but real, sitting at a value nobody can explain. One of the few honest partial ideas came from the physicist Steven Weinberg, who pointed out that if the vacuum energy were much larger, galaxies could never have formed, and no observers would exist to measure it. So perhaps we should not be surprised to find ourselves in a universe where it happens to be small. It is a haunting kind of answer, one that trades a mechanism for a selection effect, and whether it is profound or a dodge is still argued to this day. The problem endures, and it endures at the exact center of the thing we are most sure exists. Think about what this means, because it is humbling in exactly the right way. We can feel the vacuum in the laboratory. We can measure its effect on the electron to a precision that would let us split a hair 1,000,000,000,000 ways. And yet when we ask the most basic question about it, how much does empty space weigh, our best theory is wrong by a factor of 10, followed by 120 zeros. We are simultaneously the most precise and the most ignorant we have ever been about the same thing. We know the vacuum is real. We have almost no idea what it truly is at its foundation. And so let me give you back that phrase one more time, turned around, because it has carried a different meaning all along, and now you can hear it. You cannot turn space off, and you cannot yet explain why it weighs what it weighs. Both halves are true. The first half is our certainty, the second half is our ignorance. And they are the same sentence, about the same thing, the restless something that had to exist before the universe. We have proven it is there, we cannot yet read it. The ground floor of reality is real, and it is mostly unread. I find this genuinely wonderful, rather than discouraging, and I want to tell you why. Because it would be easy to hear all this as a defeat. It is not. 120 orders of magnitude of ignorance about the vacuum is not a sign that we were wrong to trust the vacuum. Every measurement still says it is there. It is a sign of how much room is left, how much of the foundation remains to be understood, how young this whole investigation still is. The cosmological constant problem is not the tombstone of the idea that something underlies our universe. It is a map of how far we still have to walk to understand that something. And the distance is thrilling, not disappointing, because it means the biggest discoveries about the floor of reality are almost certainly still ahead of us. There is a temptation, when a number breaks this badly, to throw up your hands and say we can never know. I want to resist that, firmly, because it is not true. And the reason it is not true is the most hopeful thing I have to tell you tonight. For almost the entire history of our species, the question of what underlies the universe, what came before, what the foundation is made of, was a question we had no way to touch. It belonged to philosophers and to faith, because there was no instrument that could reach it. That is no longer the case. We are, right now, in the first years of the first generation of human beings, with the tools to actually go looking, to test these ideas, to read the oldest light finely enough to tell one story of the before from another. The vacuum's weight may be a mystery, but the mystery is no longer beyond our reach. It is, for the first time, an experiment, and that is where we end, out on the high deserts and up in orbit, where that experiment is being built right now. Part 13. The first generation that can look. I want to leave you not with a conclusion, because this story does not have one yet, but with a place, and a feeling, and an honest sense of where the frontier actually is tonight. Everything we have talked about, the necessity of a something, the fields that cannot be silenced, the Big Bang as a change of state, the candidate fingerprints in the oldest light, all of it points to a single question that used to be unanswerable and is now, just barely, becoming answerable. What was the something that came before, and can we read its mark? And the reason we can even hope to answer it comes down to one specific signal that different stories of the before predict differently, a signal that would let us tell them apart. That signal is a kind of ripple in space itself, a primordial gravitational wave, set in motion in the earliest moments, and carrying, in its pattern, the signature of whatever produced it. Here is why that signal is the key that fits every lock. If our universe came from inflation, from a field rolling down its plateau, that process would have shaken space in a particular way, producing gravitational waves with one distinctive pattern. If instead, our universe came from a bounce, from a previous cosmos, collapsing and rebounding, the ripples would carry a different pattern. A collision of membranes would leave yet another. Each story of the before writes a different signature into these primordial waves, and those waves, if we can detect them, would have left a faint, specific twist in the polarization of the oldest light, a pattern woven into the cosmic microwave background that no ordinary process can mimic. Find that twist, measure its shape, and you are no longer speculating about what came before. You are reading it. The fingerprint stops being a maybe and becomes a measurement. And the gravitational wave twist is not even the only fingerprint waiting to be read. There is another one, and it is the reason you exist, which is not a phrase I use lightly. Look around at everything made of matter, the ground, the air, your own hands, and notice what is missing. There is almost no antimatter. For every kind of particle, there is an antiparticle, an opposite that annihilates it in a flash of light on contact. And the simplest expectation is that the early universe should have made exactly equal amounts of both. But if it had, they would have annihilated each other completely, leaving a universe of pure light and no matter at all. No galaxies, no stars, no listeners. Instead, for every billion pairs that annihilated, one extra particle of matter was left over, and everything you have ever seen or touched is built from that 1 in a billion surplus. Something in the earliest moments tipped the balance, favored matter over antimatter by the faintest margin, and we do not fully know what. The Russian physicist Andrei Sakharov worked out, back in 1967, the general conditions that any process would have to meet to produce such an imbalance. But the specific mechanism remains open. And here is why it belongs in this story. That imbalance is a genuine fingerprint of the earliest state, a mark left by physics we cannot yet reconstruct, written not on the sky, but into the very ratio of matter to light that fills the cosmos. Your own existence, the fact that there is something here to be made of at all, is itself a clue that the beginning was not featureless. It had structure and dynamics and a preference, and it left that preference stamped into everything, including you. And so, right now, on a high plateau in the Atacama Desert of Chile, where the air is thin and dry and still, telescopes are being pointed at the ancient sky to hunt for exactly that twist. An observatory, called the Simons Observatory, is coming online to map the polarization of the oldest light with a precision never achieved before. A larger effort, gathering observatories together under the name of a next-generation experiment, is being planned to push further still. A satellite, called Lightbird, is being prepared to rise above the atmosphere and read the whole sky's polarization from orbit. And later, in the coming decade, a trio of spacecraft called LISA will fly in formation across millions of kilometers of empty space, holding a laser steady between them, listening directly for the gravitational ripples themselves. These are not thought experiments. They are instruments being built by people alive today, aimed at the exact question you have been sitting with all night. Let me take you there, to the desert, because I think you should stand in it for a moment before we let go. Imagine you are on that plateau, 2 miles above the sea, in the dark, in the cold, in the driest air on the planet. The sky above you is the clearest sky human beings have ever stood under, and it is full of the oldest light, glowing faintly in every direction, the heat of the universe when it was 380,000 years old. Beside you, a telescope turns slowly, patiently, night after night, gathering that ancient glow and measuring the almost imperceptible twist in it. The the signature that would tell us which story of the before is true. There is no drama in the scene, only the quiet hum of machinery, the cold, the enormous silence of the desert, and a question older than every religion and every myth our species has ever told, finally, physically, wired to an instrument that might answer it. For 100,000 years, our ancestors looked up and wondered what came before everything, and had no way to do anything but wonder. You are alive in the first decade, when the wondering turned into an experiment. That telescope, turning in the dark, is the wondering made real, and the spacecraft a stranger still, if you let yourself picture them. Out beyond the desert, beyond the atmosphere. In the coming years, 3 of them will fly in a triangle across space, each one millions of kilometers from the others, farther apart than the width of many planets' orbits, and they will hold laser beams steady between them, with such precision that they can sense a change in their separation, smaller than the width of an atom. What they are listening for is the trembling of space itself, the primordial ripples set going in the first moments, the direct sound of whatever process began our universe. Think about what that means. We are building an ear large enough to hear the beginning, an instrument spread across a stretch of space so enormous that light takes many seconds to cross it, tuned to catch a whisper that has been traveling since before there were atoms. No previous generation could have imagined it, let alone built it. And it is not science fiction. The hardware is being assembled by people alive today, aimed at the exact question a child asks when they first realize the universe had to come from somewhere. There is a particular kind of humility in all of this that I find steadying rather than diminishing. We are a species that has existed for the blink of a cosmic eye, on a small planet, around an ordinary star, and yet we have worked out that empty space cannot be empty, that our beginning was a change of state and not a creation, that something had to be here first, and we have started building the machines to read its mark. We have not finished. We may be wrong about the details, but the reach of the attempt, the sheer nerve of pointing an instrument at the moment before all moments, is the thing our ancestors were doing in miniature every time they looked up. We have simply built better eyes. The wonder is the same wonder. It has only, at long last, been given something to measure. And so here is where we actually stand, honestly, as the night comes to its end. We have not answered the question, not yet. We do not know for certain what came before our universe, or beneath it. The cold spot may be a void and a fluke. The alignments may be chance and dust. The hawking points may be ripples we mistook for rings. Every specific fingerprint we examine tonight may dissolve under closer inspection, and honesty demands that I tell you the current evidence for any single one of them is not conclusive. But the deeper claim, the one this whole night was built on, does not depend on any of them surviving. It depends on the physics of the vacuum, and that physics is as solid as anything we know. Nothing is not a state reality can occupy. The fields cannot be switched off. Something was always here. The only questions left are what it was, and whether we can read the mark it left, and those are no longer questions for philosophers. They are questions for the telescope in the desert and the satellite waiting to fly. Remember the phrase we have carried all the way through. The Big Bang was the fire, not the building. And everything happening on that plateau, every night of patient measurement, is an attempt to photograph the building that was already standing before the fire ever started. We are trying to see past our own beginning, to read the something that came before it, and we are the first people who have ever had the means to try. So the next time you are somewhere dark, and you look up, remember what you are actually looking at. That faint background glow, filling the whole sky, older than every star, is not the beginning of everything. It is the light of a fire that started in a building that was already there, and the building is still here, not behind you, in a lost first moment at the end of time's long rewind. Beneath you, under the floor of the world, holding up the wave of everything you are, the something that could never have been nothing, the foundation that never needed a cause and never went away. The origin was never a moment you left behind. It is the ground you have been standing on this whole time. And for the first time in the history of anyone who has ever looked up and wondered, we have finally built the instruments to kneel down and read it.